Hi, I'm Anandarup Mukherjee. I work at the Institute for Manufacturing at the University of Cambridge in UK. Today, I will be talking about enabling IoT in the skies. The title of my talk is Intelligent Network UAVs. So, I also serve, just a brief about me, I also serve as the Vice Chair for the IEEE P1954 Standards Committee. I'm also an area expert in the IEEE ComSoc Special Interest Group on IoT for e-health. My research interests are around industrial IoT, machine condition monitoring, machine prognostics, machine learning, and UAV networks. At the bottom, these are some of my research metrics. These lovely pictures on the right you see, this is my current office, lab, and college building. So, without further delay, let's get started. I'll first talk about a quick introduction to UAVs. Most of you are already aware of UAVs, which stand for Unmanned Aerial Vehicles. They're commonly known as drones nowadays. So, what makes an UAV? From a sensing perspective, a UAV will have set of primary sensors which take care of its flight, navigation, and stability during the flight. These can be considered inherent to the UAV's operation. Secondary sensors can be attached to the UAVs to enable additional sensing capabilities of the UAVs. Some of the functions of the primary sensors include, let's say, of course, the flight control, then flight stability, different tasks which are associated with the flight controls and stability, remote communication, UAV health, and so on. Some primary functions of the secondary sensors, typically which are used, are for imaging, for basic sensing, measuring stuff, and tracking. So we'll not go into the exact details of these, but you get the general idea. So the primary sensors on the UAVs typically consist of position sensors, motion sensors, radio sensors, environment sensors, and power sensors. So the position sensors, most common of them is GPS. Most common among the motion sensors on board a UAV are gyroscopes, accelerometers, magnetometers. Radio sensors are basically engaged in looking at the signal strength, talking to other radios, Wi-Fi, and so on. The environmental sensors typically deal with sensing temperatures, pressures, and so on. And for power sensing, there are onboard voltage and current sensors which keep track of the battery levels and the energy levels of the UAV. Additional sensors are the secondary sensors on the UAV to sense parameters not necessary for flight include a variety of sensors such as spectral sensors. These can be hyperspectral, multispectral, or thermal sensors. Stabilization sensors such as gimbals and gyroscopes. So these stabilization sensors help stabilize an external attachment attached to the UAV. For example, an external camera that is attached to a UAV will have some kind of gimbal based stabilization. Typically these are expensive systems. Then there are proximity sensors which make use of ultrasonic proximity sensing or infrared based proximity sensing. Environment sensors, barometers which sense pressure, temperature sensors, flux sensors, and sound. Visual sensing normally includes camera based visual sensing, lidars, and color sensors. So broadly, these are some of the common secondary sensors you'll encounter in UAVs. So if we are to characterize the UAVs for IoT, especially for remote sensing tasks, we observe that these UAVs typically have these following characteristics. They have low communication bandwidth, they are highly mobile platforms, they have limited energy, limited load or weight capacity, complex and sophisticated controls, definitely dangerous to fly without practice. that's why like autonomous UAVs, which doesn't need a manual pilot, are safe, but then they have their own problems. What if an autonomous system, if there's an error in an autonomous system and you cannot take manual control over the UAV? So since the system is autonomous and it's flying, it's basically out of your reach, right? So there are some interesting challenges associated with those kind of systems. Then there are definitely stability issues and so on. Now if we characterize the list of UAV research areas, we see most of the UAV research areas can be grouped under the following 8 categories. They can be UAV applications, mapping-based tasks, localization, path planning, stabilization and control, swarms, UAV networks, and UAV-based imaging. Within these, there can be multiple subdomains, sublevels, and so on. So it's not directly pertinent to this talk, so I'll not cover those. But this is just a broad overview of what you can group under each of the tasks. Now we discuss some of the typical UAV network and control architectures that are possible for aerial IoT networks. So since this talk is from a networking perspective, so this next group of slides is important. So based on the type of UAVs, type of UAV networks, we can have a star configuration. So if you see in the figure, the UAVs talk to a central wireless controller. So whatever message is being transmitted to the UAVs has to go through that central wireless controller. So that's a typical star configuration. We can have a multi-star configuration where if you enhance the first figure, if you scale up the first figure, you will have a central controller talking to one UAV each, and each of these UAVs can act as a central controller for furthermore UAVs. So this becomes a multi-star architecture. We can have mesh configuration where all the UAVs talk to all other UAVs in the network, and any of the UAVs can talk to the wireless controller. So there are lots of interesting research problems like which UAV can talk to the wireless controller. So gateway selection or leader selection, these kind of tasks normally fall under this category. We can have hierarchical mesh configuration where you have multiple clusters of UAV meshes in the air, and based on whoever is nearest to the wireless controller or whoever is that leader of that mesh talking to the wireless controller, you can have multiple configurations that talk downwards to the ground-based controller. Now from a control-based perspective, we have the following UAV control architectures. A human can control the UAV wirelessly, so the human is directly responsible for the UAV's flight. In another configuration, you can have a human in the loop, but the UAV is mostly automated. Like the control is mostly pre-fed into the UAV controller. In case of an emergency, the human can take control of the UAV flight. The third architecture is the whole system is automated. There's no human involved in the control of the UAV's flight path. It can work based on some predefined GPS locations or some sensing parameter or some environmental parameters. That basically depends what's the end goal of that architecture. The fourth architecture could be the whole system is automated. A wireless controller talks to a wireless controller on the ground talks to one of the UAVs, which then acts as a swarm leader for a group of multiple UAVs. So whatever controls or let's say formation plans are sent to the UAVs flying above you are sent through one of the UAVs. So one of these UAVs is the swarm leader, which forwards the message from the ground to the other UAVs, and the other UAVs behave accordingly. Next architecture, the fifth one, is the ground control station is now mobile. Different set of challenges associated with this. Earlier, the ground control stations were mainly fixed. So now the ground control station is moving, the UAV swarm is moving, and there are problems associated with who is going to be the swarm leader, or how are you going to choose the swarm leader. There are problems associated with the communications quality and handoffs and these kind of issues, since the ground control station is also now mobile. And lastly, we can have an automated UAV, but on the ground plane, the UAVs need really precise sensing. So one good example is you have lots of ground-based, there's a wireless sensor network deployment on the ground, and the UAVs have to go to each of these wireless sensor network nodes to collect data or some information from these nodes and move to the next node. So how the UAV does it is the algorithm, or it's the task of the automated control station. So this adds different levels of complexities to the sensing task. Now, as data handling forms a core aspect of IoT, I'll take a few examples of how, through proper data handling in these aerial IoT networks, these approaches can be made more robust. So let's say this is computing meets the systems, the flying systems. So I will take 3 different types of approaches that can address one aspect each of data handling in these aerial IoT networks. The first task or approach deals with reducing network data transmission. The second approach deals with selection of routing path based on multi-parameter optimization. And the third approach addresses distributed processing or handling of data within the UAV network. So the first task looks into how to reduce data traffic transmitted over a network between a UAV and a remote server or a control station. The aim is to facilitate reduced network utilization during network control of the UAVs. We proposed this as part of a conference work in 2018. So the brief gist is we downsampled the position sensor values of the UAVs, like when we are collecting sensor data from the UAVs, so accelerometers. So we, instead of sending 10 values, we sent only 5 values. So that's like we downsampled the sensed values on the UAV, and we sent this reduced values over the network to a remote control station. So since we downsampled it, we have reduced the network traffic, but the critical problem now is, since we are considering lesser sensor data, we have lesser information. That basically puts the UAV flight at risk because it needs really precise control values for its controllers. Let's say it has a PID controller, right, which deals with its stability. So if you reduce the data values getting fed into that controller, you're risking the whole flight stability. So what we did was we used a LSTM based method to predict the missing sensor values at the remote server. So recall that we are sending reduced data values to the remote server, which now has a LSTM based module. LSTM stands for long short term memory. It's it's a deep learning approach. So where we can forecast trends based on past values and behaviors. So whenever a data packet arrives at this LSTM module at the remote server, it can predict the next set of values. And we realized that this was a good way of reducing network traffic, but the drawback was it kind of increases the computation. So you need increased computation at the remote server. So there's a trade-off. Let's have a quick look at it. This work was called Sense, Predict and Actuate, which was presented to the IEEE WCNC conference in 2018. So now look at the second figure, the bottom figure. So even if we downsample one sensor reading and predict it at the remote site, so let's say it's in a format such that one actual reading is being transmitted, then a blank, then another actual reading, then another blank, and so on. In this, for example, in the second figure, you see those box plots, right? So this transmitted actual values interleaved with missing sensor values to the drone's remote server, and this enabled us to save about 50% of the network traffic for each drone, because you're knowingly skipping or missing out every alternate value. So how does it affect the performance? Before we go there, so this reduction in the TDMA based access time is achieved by downsampling the sensor readings on the drone, and the remote server predicts whatever is the missing value, and then this reconstructed signal is fed to the controller, and the control signals are fed back to the drone. So we realized that if you see the blue line, this is what the typical network on which the drone was connected would support. So we realized for each similar drone, the network was able to support 33 drones. If we downsample every alternate value, so you have one actual value, one missing value, one actual value, one missing value, the network would be able to support 58 drones, where normally it was able to support 33 drones. So that's a massive jump, right? To make things more interesting, if we have two actual values, one missing value, two actual values, one missing value, the network support capacity becomes lesser to 52. If we have three actual values, one missing value, and so on, the support capacity is 45, and so on. Right? So this was a really interesting work. Now, if we move to the next task, we'll look into how a decentralized drone swarm can make use of data offloading part selection strategy to maximize its functionality and longevity. We used a distributed reinforcement learning feature, and we had trained reinforcement learning models to achieve reward maximization. At first instance, if we look at the leftmost figure, at first instance, if the offload path selection is based on drone residual energy, number of tasks, and processing requirements. So based on these parameters, the selected drone offload path, if you see this, bottom is the source and the top is the target. So this goes from D1 to C1, B2, A3 to A4, which is the target. At the next instant of time, if you are using a multi-arm bandit based approach for utility function, in the next figure you see this offload path automatically gets changed depending on what is the available processing power, what is the available energy in the whole network. So to conform with the multi-arm bandit reward criteria, we restrict the utility function value in the range of 0 to 1. For this, we use a sigmoid function. Now, the approach allows for higher energy savings in an ad hoc edge UAV swarm, which also allows for more uniform task distribution and more uniform UAV selection in the network, which therefore allows for reduced wear and tear of the constituent UAVs in the network. The selected offload path using our proposed distributed strategy ensures the continuity and survival of the chosen path even for larger data sizes. So if you're offloading larger data using our proposed method, those larger data sizes can also be accommodated quite reliably. So the reward function was bounded between 1 and 0 and is represented as a sigmoid function. This shows a picture of the top right image shows a picture of two drones flying in the drone network we tested it on. These plots show that the reward starts stabilizing over larger episode numbers during training. With respect to the trend line, you see the red trend line it starts stabilizing and the rewards start maximizing, right? In this next set of bar charts, the left bar chart shows the multi-arm bandit based training time and the number of bandits generated within the small subplot within it. We see that these increase exponentially as the number of grids per UAVs per location keep increasing. The right bar chart shows that if we limit the number of experiments and episodes, we can achieve feasible execution time of the multi-arm bandit even at edge-based systems. Further, large-scale emulation of our SOM tuned by real-life hardware metrics collected from multi-rotor UAVs in flight, it shows the conservation of collective SOM network energies, which outperform approaches such as simplest shortest path approach, other offload-based path selection strategies. And the multi-arm bandit based selected path may not be shortest, but it is more energy efficient and processor friendly. We also see that with the provision of replenishing energy during the flight, if that provision is made available to these UAVs, the configuration with charging facilities which can replenish the energies while the UAVs are in flight, they start outperforming the chargeless ones for larger grid sizes. So when the tasks are more spread out, the drones are used more intensively. So takeaway is have a charging replenishment facility. And finally, we move to the third task, where we explore the possibilities and the impact of processing tasks in a distributed manner within the aerial SOM. So for fast and efficient sensing and processing of resource-intensive data aerially within the network SOM, we proposed a Nash bargaining-based weighted intra-edge processing offloading scheme, which helps to distribute the load appropriately between the constituent UAVs in that whole UAV network. So which UAV gets what part of the processing based on how much processing it has got left, how much energy it has got left, and other parameters. So we strategize this Nash bargaining game to decide how much to offload where. So this shows the UAVs in a coordinated flight pattern forming the aerial network. As an example, if you see that red node, it senses something visually on the ground. Now, since it's recording a video, as the nodes are constrained, all the aerial nodes are constrained, the red node offloads parts of the video frames to other UAVs in its network for further processing, like image processing or computer vision and different tasks, using our proposed distributed aerial processing protocol. We tested the performance of this distributed processing for different configurations such as star, mesh, star with server, mesh with a ground-based server, and so on. So in this third figure on the left-hand side, you see that for the initial few cases, the proposed distributed aerial processing outperforms mesh configurations, which is rather expected. But interestingly, as the number of UAVs start to increase, we see that the proposed approach starts becoming comparable to the star configuration, which is the best scenario possible. Now, as the collective processing power also increases, because as the number of UAVs increases, the collective processing power keeps increasing because you have more resources available to offload your processing to. As you can see, like with the increase in number of UAVs, the processing power keeps increasing. So this scheme helps achieve a better scalability and reduce processing delays for intensive processing tasks. But on the flip side, would need a much more larger number of UAVs. So these were the three tasks which showed how you can have reduced network traffic. This is not the only solution, but these are examples of approaches you can take to address data in the aerial IoT network. So reducing network traffic, proper offload path selection to ensure more data survives in the aerial network, and the third approach was to increase the collective processing within the aerial network. So mind you, we are in the third approach, we had no ground control station. So whatever was done, whatever processing was achieved, was within the aerial network. Like everything, all the nodes were flying, all the drones were flying, and whatever processing was happening was within the aerial network. There was no ground server, no connection. So that's what made it more interesting. So that was it for my talk. Thank you.